We are going to. Okay. Good morning, everyone. I'm Ju. Happy to see you all in the CMSA GR seminar. Today, we are happy to have Dr. Chao Liu from Huazhong University of Science and Technology to give a talk. The title of his talk is Global Existence of Stability of Discrete-like Solution to the Einstein-Yang-Mills equation in spacetime of dimensions not less than 4. Okay, let's welcome Dr. Chao Liu.
Okay, thanks, Joe's invitation, and I'm very glad to have this opportunity to give a talk on our recent work. Our recent work is about the Einstein-Yang-Mills equation, and we will talk about the theta-like solution stability problem. And for this work, we care about the dimension n is bigger than 4 or equal to 4. This work is the joint work with Todd Oliynyk and Jinhua Wang. Okay, let's get started. Before we get started, since our topic is about Einstein-Yang-Mills equation and also about the theta solution, so let's review some basic concepts. The first one is the Einstein-Yang-Mills equation. Einstein-Yang-Mills equation is usually given by this system. The first one is the Einstein equation. I believe everyone will be very familiar with this one. And the second and third one is the Yang-Mills equation. In this equation, this G tilde AB is the Einstein tensor. And this T tilde AB is the stress energy tensor. And here, this term is, here lambda is a cosmological constant. And in our paper, we only care about the positive cosmological tensor because we are thinking about the theta space. So it's strongly related to this lambda bigger than 0. If we consider the Yang-Mills field, then the stress energy tensor will be taken in this form. I believe most of the audience must be very familiar with Yang-Mills field, much better than me because I only learned this last year. So the Yang-Mills field is about it's a fiber bundle. You know, we can use a fiber bundle language to describe it. So usually in this Yang-Mills theory, we will have a gauge potential, this A tilde, and we also have the curvature. It's also known as the Yang-Mills field. We denote it by this FAB. And this FAB have the relation with this A by this formula. And they also have the Bianchi identity. In fact, is the third Yang-Mills equation. So this is our setup. And the second concept is about the theta space. The theta space usually given by this metric. This is one global expression of the theta metric. And the theta metric is an exact solution to the Einstein equation for the vacuum, of course, the vacuum Einstein equation. In this expression, this H is related by this formula related to the cosmological constant lambda and the dimension n by this one. Okay. This H bar is the standard metric on this surface, n-1 surface. So in our paper, in this talk, we will use a conformal picture to describe our stability problem. So first, we should do the conformal transformation of this theta space-time. So how do we do that? It's actually very easy because we only need to find another new time variable if we denote it by t, then we only need to find some relationship between t and this tau. How to do that? We can let this d tau just equal to h cosine square h minus 1 tau dt. You can see if no, there's no square. You can see if we let this relationship here, then we insert it into this metric, then we will have a conformal factor h squared cosine h minus 1 tau square. And then we can let this one as our conformal factor. Then this metric can be written in this form: GAB tilde equal to some e to the 2 phi and the conformal metric AB. So if we want this relationship hold, then usually we have to have this transform like this one: t equal to this relationship to this tau. This tau known as a conformal time in our talk. Conformal time. No, this tau is a physical time, and this t is our conformal time. This is physical time. And here, there's the GD represents the Goodmanian function. It's defined by this function. We got this very naturally because you just, like I said, you just need to solve this equation. For example, dt equal to h cosine h minus 1 tau d tau. If you solve this simple ODE, then you can get this t and tau have this relationship by the Goodmanian function. Okay. Like I said, if you have this time transformation, then we can transform the theta spacetime to the conformal theta spacetime. The conformal one is this one. And in our talk, we will use tutor to represent all the variables in the physical picture. And we use this variable without tutor to represent the variables in the conformal picture. And our conformal factor eventually becomes this one. And you can see this one is behaves very like the minus log t. Okay. There's some very important remark on the conformal spacetime. You can see we have did this time transformation here. And in this transformation, you can see if your physical time is minus infinity to the plus infinity, I mean this tau, this physical time belongs to this region, then you can, from this relationship, you can get your conformal time to belong to 0 to pi over h. If you draw a picture, this time transformation is something like one. This is t and this is tau. Then your picture will be like this, and this line will be very close to the h over pi. So this time transformation is a decreasing function. And if your tau goes to positive infinity, then this t will goes to 0. This is 0. So that means your physical time go to the infinity, then your conformal time will go to the 0. That means you map the future infinity to a zero surface. So you map the future time like infinity to the boundary components like this one. Okay. And after this preparation, I think we can give the main theorem. But before the main theorem, I should say something about that. In our main theorem, we will represent every variables in the physical picture. And but in fact, in our main proof, we use the conformal picture to describe everything. So we use conformal variables. Why we did this? Someone may ask why we don't describe our. Sorry. The connection is not good. Is there any problem?
Professor Yu? Professor Yu?
Sorry, is there anything? Okay.
Okay.
So is there any question? Okay, I will continue. In our main proof, we will use a conformal picture, and all the variables we use is a conformal variable. Someone may ask why we don't describe our main theorem by the conformal variable. Okay. The reason why is based on our proof. I will explain later. Okay, before go to our main theorem, let's give a very, very brief review on the de Sitter-like stability. The first group is dependent method. The first one is Friedrich in 1986. He proved the four-dimensional de Sitter space stability for the vacuum Einstein equation. His method is his conformal method. And then in 1991, he generalized his method to the four-dimensional de Sitter-like stability for the Einstein-Maxwell-Yang-Mills field. In fact, our paper just want to generalize Friedrich's this work to the n-dimensional de Sitter-like solution. Okay, and in 2005, Michael Anderson has generalized the Friedrich's this result to any dimensional for any even dimensional de Sitter space stability for the vacuum Einstein equation. His method based on the Pfefferman-Graham tensor. So all these works are strongly dimensional dependent. Until
may I make a comment?
Sorry?
That I'd like to make a comment that
okay.
Anderson's paper has a gap. I mean, the idea is very nice, just he has the right equations, but his existence problem, proof of the problem is actually incomplete. And that has been fixed recently by Wojciech Kamiński. There's a preprint.
Sure. I know that. We write it down in our paper, but we don't list it here. So it's very, very brief.
I just want to point this out.
Yeah. Okay. Yeah. Okay. Then in 2008, Hans Ringstrom has a new method to prove the all-dimensional de Sitter-like stability. I mean, all-dimensional, in fact, it's just n bigger or equal to 4. His equation is Einstein scalar field. And then Sedberg generalized Hans Ringstrom's result and extend his result to the Einstein-Maxwell scalar field. But they use the Lorentz gauge for the Yang-Mills field. And in our paper, we want to use the tempo gauge. And I don't know if Hans Ringstrom method can also do for the Einstein-Yang-Mills field. I think it will work, but we haven't tried. Okay, so we now just fix to our method. Okay, and there's a lot of works about the theta-like stability for the Einstein couples, some fluid equation like Einstein-Euler equation. There's a lot of work. It's very hard to list them all, so I only list a few of them. First, Roniansky, Jerry-Speck, and Lubo, Kroon, and Haddock has proved the FLW stability for linear equation of state satisfy this requirement. Of course, there's a lot of papers to finish this work. And then Todd Oliynyk has another method. He used a function formulation of the Einstein-Euler system to solve the similar problem. And then we use this function type system to solve several problems like the cosmological Newtonian limits and also for various nonlinear equation of states. We can do that for many kind of fluid, but there's actually a lot of gap in the fluid, in the equation of state, because for some index, we cannot prove it. And we think there must be some instability related to the Jinhua instability. In fact, I'm working on that recently. Okay, there are also some other non-de Sitter-like stability. Of course, there's too many works. It's very hard to list them all. Okay, maybe let's just go to our main theorem. But before the main theorem, we have to introduce some variables to state our theorem. In our theorem, we will use the 3+1 decomposition of the Yang-Mills field. This 3+1 decomposition is, we use this time direction defined by this one. Then we decompose this Yang-Mills field F to the time direction and project to the hypersurface, and we call this variable E tilde, and the F variable project to the hypersurface, we call it H tilde. I just want to mention, I just want to point out here, in this time direction, we use this G tilde AB to raise the index. But in our proof, in our global stability proof, we will use another time direction. Why we should do that, I will explain later, but please just remember, we use a different time direction. In the theorem, in the statement of the theorem, we use this one, but in the proof, we use another time direction. And the temporal gauge in the main theorem, we gave it by this A tilde TA equal to 0. It's the component of the A on this direction is equal to 0. But in our main proof, we use A on the other time direction equal to 0. So there will be a gauge transformation involved. And the wave gauge we will use is this E tilde A equal to 0. And this E, this Z is defined by this long formula. Why we use this long formula? The purpose we do that is because we will use the conformal picture to prove everything. So eventually we will do a conformal transformation, transform this E tilde to another conformal Z. In that conformal Z, if we choose this source term like this one, then in our function formulation, we can get a good expression. Otherwise, there may be some T square 1 singular term involved. We don't want that. So we design this wave gauge just like this to kill some bad terms. So this is our purpose. Okay. After introduce this 3+1 decomposition of the Yang-Mills field, then we can state our
question.
Okay.
Is it obvious that one can always achieve this gauge, or one needs to be near to the theta? What's the situation here?
Sorry.
Is it clear that this gauge can always be chosen, or this needs some restrictive conditions, or?
No, it's not very clear. It's when you, when we, our purpose is to transform our Einstein-Yang-Mills equation to a function formulation. So if you choose another wave gauge, at least this wave gauge can kill some bad terms in our.
Yeah, and I understand that, but can you choose this gauge? I mean, so that's the question.
No, you cannot choose it freely. There's some restriction, and this restriction comes from to kill the bad terms in the function formulation.
If you're on the theta spacetime, high dimensionals, can you always find a conformal factor which gives you this?
Yeah, we can. If you define this, if you define this wave gauge like this one, and you choose this conformal factor like before, like here, then you can always
it's satisfied.
do that. Yeah.
Okay, so in other words, it's one expect is going to be satisfied for small.
Yeah.
Perturbations, or.
Yeah.
And is this something that you can prove, that for this metric which is close to the theta you can find this gauge?
No, you shouldn't. It's not like the conformal method by Friedrich. Here, our idea is to choose this conformal factor, then formulate Einstein-Yang-Mills to the function formulation. And this thing you can always choose. After you choosing this, choosing this conformal factor and the wave gauge like this one, then your function formulation will you can get a good function formulation. Then you can use that.
Okay. Thank you.
Okay. Thanks. Okay. Let's state our main theorem. The main theorem is actually very simple. Simply speaking, it just means our initial data is close to the theta space. Of course, our Yang-Mills field should be small, very close to the theta space. Then your perturbation, your evolution of this Einstein, the solution of the Einstein-Yang-Mills equation will be also very close to the theta space. This is our results. Of course, in the tempo gauge and the wave gauge we gave before. And more specifically, the Yang-Mills field will be very small. And the metric will have this decay. Here we have this weird coefficient, but this coefficient, you just notice is just the conformal time t. So this estimate means this metric close to the theta metric in this rate.
So the data are on conformal infinity here. It's this.
No, this data in some finite.
Is in space time or at the boundary?
In space time.
Okay, thanks.
Yeah. Okay. There we write it as 0. This is use the physical time. Physical time tau equal to 0. later on, we will use conformal time. So it's kind of confusing. Okay. I want to give some remarks on the main theorem. In this main theorem, you can see we describe every quantity in the physical picture. And we use the wave gauge and the tempo gauge like we defined before here. But in our main proof, we will transform this physical picture to the conformal picture. And if we do the conformal transformation, this wave gauge will become this wave gauge. It's just based on the conformal picture. But there is something unexpected. It's the tempo gauge. If we did the conformal transformation on this tempo gauge, we cannot get this tempo gauge. But in our main proof, we will use this tempo gauge. So in order to connect these two tempo gauge, we have to do some estimate the gauge transformation. But why we cannot use the same tempo gauge in our proof? This is because in our local, because in this talk we will mainly focus on the global existence and stability. But before this, we have found out the local existence of the Einstein-Yang-Mills equation. There's of course a lot of methods to prove the local existence, but we want to find some methods to compatible to our global proof. So in our local existence of the Einstein-Yang-Mills equation, we have to choose this tempo gauge because maybe I will explain later. There's some reason we have to use this one. And in our global proof, we have to use this tempo gauge because if you use this tempo gauge, your formulation will be very clean. And you can go to the function formulation. But if you use this one, maybe you can still get the function transformation, the function formulation, but the equation will be very ugly. There will be very more bad terms. Okay, so that's the main purpose why we state the main theorem in the physical picture, but our main proof using the conformal picture. I will go back to this repeatedly because it's very important in our proof. Okay, and in our main proof, we will use the function formulation. This is our main tool. So in the rest of our talk, I will focus on this function formulation. This picture gives the main idea how to prove this long-term stability of the Einstein-Yang-Mills equation. You can see there's involves two pictures. The first picture is this physical picture, and the second one is a conformal picture. And we will use two sets of variables. In the physical picture, we will use some physical variable, and the conformal picture, we use conformal picture. To connect these two pictures, we use some conformal transformation and gauge transformation. We want to use the picture one, I mean the physical picture, to get the local existence, because in this picture, we can prove the Einstein-Yang-Mills equation is totally equivalent to some symmetric hyperbolic system. This we can prove. But in the second picture, in the conformal picture, we will prove some conformal Einstein-Yang-Mills equation will imply the function system. But on the contrary, the function system will not imply the conformal Einstein-Yang-Mills equation. So this is something very bad. I mean, equivalent and imply here, the meaning of that is when I said Einstein-Yang-Mills equation is equivalent to the symmetric hyperbolic system. I mean, if Einstein-Yang-Mills equation have a solution, for example, we call it solution 1, then this solution 1 will also solve the symmetric hyperbolic system. And if we have another solution to this symmetric hyperbolic system, we call it solution 2, then this solution 2 is also equation of Yang-Mills equation. But for here, we only have one direction. That means if we can solve this conformal Einstein-Yang-Mills system, then this solution will also a solution to the function system. But on the contrary, it's not right. I mean, if we have a solution to this function system, then we cannot say that solution also solve this conformal Einstein-Yang-Mills. So this is bad. But in the picture 2, we can only done to this level. Okay, our idea is because we know function system very clearly, and using the function system, we can get a global solution to this function system. But we cannot say this function system also a solution to Einstein-Yang-Mills system. So how to fix this? We just need to use the local existence. If we get this solution, this local solution, then that means we have a local solution here. And this solution must solve this function system. And the function system can only have one solution. So this solution must solve the function system. And we can, then we research this function system, we got some good estimate on this solution. We got some estimate on the solution of the function. Then use this estimate, we can see this solution, this local solution is bounded. Then if we know this solution is bounded, then we know in this local solution is bounded. Then use the continuation principle, we conclude this local solution can be extended to the global, and we use this estimate to get some information on it. Then we can prove the stability. This is our main idea. It's twisted, involves several systems, but at least for now, we can only do it like this one. Okay, because the function system is very important, so let's just briefly talk about this function system. Our function system is something like this one. This involves some singular term 1 over t here. And we have a lot of restrictions on the coefficients b and g. But why we need these coefficients? I will give you a very simple toy model to explain why. And if we have a system like this one, then we have a global existent results. We have a theorem to state the behavior of this system. The theorem is given by Oliynyk in 2016. The theorem is that a solution to this function system should satisfy this estimate. And if it satisfies this estimate, then this solution can be extended to the global. And here, I said global means, because you say this, if t equal to 0, this term will blow up. So when we consider this system, we only fix our time interval from some constant, like for example, -1 to some 0. We only consider t belongs to here. In this system, our time infinity is in fact this 0. That's why we need the conformal transformation to pull the positive infinity to 0. That's the reason why we want to use this conformal transformation. Okay, this is our main theorem for the function system. Why this theorem is right? I just give you a very simple toy model. You can consider some ODE like this one. It's very simple. Then you can just move this term to here and integrate this ODE. You can get some estimate like this one. And this one is very similar to this one. And in fact, our system like this one, why we want all these conditions? Just because we want this system is very like this simple system, this simple ODE. That's our main reason to give some restriction on the coefficients. Okay, this is the main idea. And of course, if you observe this simple ODE, then you can get some accurate estimate on this U. Of course, you can solve this U. But in our paper, we don't need that kind of accurate result. We only need this estimate is enough to conclude the stability. But if you want to get some asymptotic property, you should go forward. Of course, Oliynyk has already given some asymptotic estimate based on the solution of this model. You can go check that paper. But in our proof, we only try to prove the stability, nothing about the asymptotic property. Okay. Because we want to use this function system, so we have to transform the physical field to some function field. In order to transform the physical field to this function field, we have to do 3-step transformation. The first transformation is a conformal transformation. Like I said before, we want to prove the whole things in the conformal picture. So the first step is we do the conformal transformation like this one. And the second step, we decompose the metric to the 3+1 decomposition. We did it like this one. And then we introduce some function gravitational field variable. Why we introduce something like this one? It's because we want to get the function system. If you don't use some variable like this one, your system after the conformal transformation and the 3+1 decomposition, your system may involve 1/t² terms. It's very bad. I mean, in this function system, it may be involved 1/t² term. So it's very bad. But if you choose the variable like this one, then you can get the correct function formulation. And also for the function Yang-Mills field, we will introduce some decomposition like 3+1 decomposition like this one. And you may notice there will be some E, this curly E. I will explain why this variable appear later. I should mention something. It's about this conformal transformation. We did this, but it's not the optimal transform. I mean, the optimal transform should be something like this. We did this transform because if we have this conformal factor here, then our formulation will be easy to verify. But if you let the conformal transformation like this one, then your formulation will be very hard to verify. This one is restrictions on. Okay. Okay. But in the end, we have to correct this conformal transformation to get some posteriori estimate to improve our results. I just mentioned that here. Okay. The second part is about the function formulation of the Einstein-Yang-Mills system. Because this is the main part of the proof, so I will talk about focus on this part. That means we will transform the conformal Einstein-Yang-Mills system to the function system. Go to this step. Okay. The first one is the function expression of the Einstein equation. First, the physical Einstein equation is something like this one. Then do the conformal transformation is the standard result. The conformal Einstein equation will be like this one. Then we introduce the conformal wave gauge. This conformal wave gauge is just the physical wave gauge after the conformal transformation. This physical wave gauge we have given in our main theorem. We just mentioned that. So this ZA conformal wave gauge just using this Z tilde A after a conformal transformation, you can get this one. You have to very carefully choose the source term of this wave gauge, because if you choose wrong, then your function system will fail. You will get the, like I said before, you will get the 1/t² term there. So why we choose this source term like this one is because we want to kill the 1/t² term. That's our purpose to choose this one. Okay. Then we can write the Einstein equation to the reduced Einstein equation by adding these two terms. You can see, because we choose the wave gauge, the conformal wave gauge, ZA equal to 0. So this term actually becomes 0, and this term also becomes to 0. And if we add these two terms here, then we can also kill the bad term 1/t² in the remainder terms. That's the reason why we add these two terms in our Einstein equation. So in summary, if we want to write the Einstein equation to the function formulation, we should care about three key choices. We have to carefully choose the conformal factor. Conformal factor is something like this. If you choose a conformal factor like this, then you can kill some 1/t² term. And you have to choose your wave gauge carefully. Like I said, the source term Y, you have to choose it carefully than to kill the 1/t² term in the remainder term. And also, you have to choose the variables very carefully. Like I said before, the function field, the function variable. If you choose wrong, then you got the 1/t². So all this choice based on to kill the 1/t² terms in the remainders. That's our purpose. So I just list some formulation in our proof. Firstly, you can write this conformal Einstein equation to this form. Then do the 3+1 decomposition. Recall the function field. Recall the function field using the 3+1 decomposition. Then you can decompose the Einstein equation to this system. I just quickly browse this system, just give you some feelings. You don't need to care about them much. Okay. In this system, there are always some bad term. You know, this tangent HT is behave like 1/t, and the sine square HT behave like 1/t². So you can see there will be some bad term. We want this kind of term, but we don't like this term, because this 1/t² is not in our function formulation. It's behave very bad. We cannot handle it. So we want to Q every term like this one or this one. So that's why we introduce our variable lambda plus 1 equal to something t multiply something like here. Like here. We want our lambda plus 1 behave like some constant t m. This t will Q this 1 over t square will Q t here to get the 1 over t term. This is our purpose. And I also should mention something is in this function field, there are some constant to be determined, why we choose this constant? Because this constant depends on the dimension. Because our proof is about the any dimension for n greater or equal to 4. For different dimension, we have to choose different constant here. In fact, for n equal to 4, we choose one set of this constant. And n equal to 5, we can choose another set of constants. And for every dimension bigger or equal to 6, then we can choose a uniform constant size. This is a trick how to handle all the dimension. Okay. Once we did that, then we can try to write down the Einstein equation to the function form. You know, the function formulation is just a singular symmetric hyperbolic system. So we have to symmetrize this system to a first order system. So in order to symmetrize this, to write this second order PDE to the first order PDE, there is some standard method we can use. But in our paper, we introduce some symmetrizing tensor like QEDC. It's defined by this one. Why we want to introduce this kind of tensor? Because this tensor will help us to, it's very important in the Yang-Mills equation. I will explain later, but for the Einstein equation part, it's very useful too, because if you use it, then this kind of term in our equation before will have 2 extra terms like this one. And this 2 term can be replaced by the background Ricci tensor. This is the benefit of the symmetrizing tensor here. But for the Yang-Mills equation, it's very useful later, okay? So after we use this symmetrizing tensor, the Einstein-Yang-Mills, the Einstein equation can be symmetrized to this formulation. You can see this one is the 1 over t term in our function formulation. And all the coefficients is something like this one. I list them, but it's not very important here. I just want to point out this 1 over t term here, 1 over t term, the coefficient metric is something like this one. And in here involves some constant to be determined, like I said before. In fact, the decay rate of the variable is dependent on this curly B matrix. And all these variables will help you to determine the decay rate for the different dimension. Okay. Next, let's talk about the function expression of the Yang-Mills equation. First, you can write down the conformal Yang-Mills equation in this form. After you write down this, it's in the conformal Yang-Mills field, then we want to write we can express this unknown, this covariant derivative by the background covariant derivative, then you can write the conformal Yang-Mills equation into this form. Next thing is we want to write this Yang-Mills equation to the function form. I mean, first you want to get a symmetric hyperbolic system, involve some 1/t term here. So first we want to ask, how do we symmetrize this equation? How to write it to a symmetric hyperbolic formulation? So now we can think, can we use the symmetrizing operator Q, like in the Einstein equation? The answer is yes and no, because firstly, if we try to use this Q operator to symmetrize this equation, you can find there's some benefit here. If you project this equation to the hypersurface and you use this Q tensor here, then you will have some extra term in your conformal Yang-Mills field. And this term, you can replace it by the second, this Bianchi identity. Then your Yang-Mills field will become a very nice formulation. From this formulation, it looks like a symmetric hyperbolic system, but there's something bad. In this coefficient matrix, we have an actual term to break the symmetry. So it's not a real symmetric hyperbolic system. So in order to solve this question, how do we do that? We introduce another variable, this one. In fact, just observe this term, and you can see this term should be multiplied this one, this CEF. So this gives you a hint if you write it like this one. So you can think if we introduce some new variable, maybe we can remove this bad term from this matrix. So we introduce a new variable like this one, and it's in fact just this one, okay? So if we introduce this new variable and we complement some new additional equation, in fact, this equation is also included in the original conformal Yang-Mills equation, but in this step, when we got this equation, we lose some information. So we just add this losing information in. Add this equation in, then we can get a very nice symmetric hyperbolic system with this singular term here. So this system is a function system. This is a function system. So the trick is we introduce a new variable to symmetric this system, but here is something bad, because let's say it in this way. Okay, let's see it in this way. We got first we started the conformal Yang-Mills equation, then we get this symmetric hyperbolic equation. But if you have a solution to this equation, then this solution should solve this one. It's clear because you get this equation from this one. So this solution should solve this one. But this solution may not solve this one. If you have a solution to this function system, then this solution may not solve this one. This is because you introduce a new variable. So you have to add this relationship to your system. This equation, this identity with this equation is totally equivalent to the conformal Einstein-Yang-Mills system. But if you remove this relationship, just looking at this symmetric hyperbolic system, you cannot get a solution which is also solve the conformal Einstein-Yang-Mills system because you lose some information here. That's the reason why we have to have some conformal, we have to have a solution to the conformal Einstein-Yang-Mills, then we can see that solution is can be extended by this system, okay? So, okay. So in the end, we can transform the conformal Yang-Mills system to a function system. Then at the end, for now, we have solved this part. I mean, to transform a conformal Einstein-Yang-Mills to a function system. Then now, this function system give you a solution, But we cannot say this solution also solve this conformal Einstein-Yang-Mills. The reason is because we lose some information here. So how can we say this solution is also a global solution to the conformal Einstein equation? We only need, if we already have a solution to this system, then we can say these two solutions must be equal, because this function system can only have a unique solution. So they must be equal. This is our idea. So the main proof is something like this. First, we prove a local result to the Einstein-Yang-Mills system. This has been done by the Shukri-Barupa long time ago, but he used the Lorentz gauge. In our paper, in our previous paper, we give a new symmetric hyperbolic formulation to the Einstein-Yang-Mills equation. It's very similar to the symmetration I talked here, but it's also have some different, because in that paper, we choose the time direction defined by the capital T, not the nu. Remember I said before. Anyway, my time is up. So simply speaking, we only need that time direction is slightly different the time direction in the long time scheme. So, but if you choose that time direction to do the 3+1 decomposition, then you will have this Einstein-Yang-Mills equation is totally equivalent to the symmetric hyperbolic equation. Their solutions are the same. So if you have a solution to the symmetric hyperbolic system, then that means you have already solved the Einstein-Yang-Mills system. That's our idea in that paper. So in that paper, we have a local solution. And in this paper, we have a local solution to the function system. Then we can see these two solutions is the same. And using the function system, we can extend this solution to the long time, and we can prove the stability. Then because these two solutions are the same, so that means your original local solution can also be extended to the long time, and they are stable. That's our main proof. Okay, thank you.
Okay, thanks the talk of Dr. Chao Liu. Any question or remarks?
I have a question.
Okay.
So the existence part here, you're just using as a black box the theorem of Oliynyk as before. That's how it works, or?
You mean the local?
So once you formulated it in this form, you just apply a result, previous results of Oliynyk for the global existence?
Yes. We use that Oliynyk's results only for this function transformation, but we revised it a little bit. I mean, this theorem, we use this theorem. Okay. Oh, here.
Right. So you can just use it as it is, or do you have to do something more with?
The key idea is here, but because in our case we use some geometric formulation. So it's, I mean, the key idea is totally the same, but the expression is a little bit different. Only for the function system, we use this result.
And then you need some stability, right? It's a small data, is it, the theorem?
Yeah.
So use a version of this with stability.
Yeah.
Okay.
Yeah,
thanks.
but for the Yang-Mills part is totally different.
Sure, yeah, thank you.
Okay.
I have a quick question.
Okay.
You mentioned that when you transform the conformal Einstein-Yang-Mills equation to a function system, some information is lost.
Yeah.
I don't know why it's possible to add another condition or equation. Where is the freedom?
I mean, okay, it's here. I'm not sure I understand, but maybe it's here. Okay, let me see. Like I said here, because we transform the Yang-Mills system to this function formulation here.
Yes.
If we want to transform it to this symmetric hyperbolic formulation, then we have to introduce this new variable.
Yes.
Right? If we introduce this new variable, that means this new variable with this whole equation is equivalent to the conformal Yang-Mills system. But when we solve this function system, when we use the Oliynyk theorem before, then we cannot use this definition in our system. That means we have to forget the relationship between this curly E and this E. So we lose some information. We lose,
okay.
This is losing information. But this and usually you have to recover this information by the constraint equation. But in our formulation, this cannot be recovered. I don't know if we can do that because it's too hard, so we don't do that. But for the local existence, we slightly change our time direction. Then we can recover this constraint with our evolution equation. So in that time, their information are totally equivalent. So in the local existence, if you choose your time direction in that t direction, and you use the wave gauge, you use this wave gauge, then you can get your Einstein-Yang-Mills system is totally equivalent to the symmetric hyperbolic. But in this formulation, this information has lost. I don't know how to recover it. Maybe it's
so this method
equivalent. Okay. Yeah.
This method just happen to hold for Yang-Mills equation. Does it hold for other equation?
No, I don't think so. But I think this method can be used for other system. If some system is not symmetric, if we want to use this symmetric hyperbolic equation, so maybe we can introduce some new variable. Then we forgot the relationship between the variables. And if you give the initial data correctly, you can solve this as a constraint. Then maybe you can use it.
Okay, thank you.
Okay, thanks.
Any question? Okay, if there's no question, we will end the Zoom meeting of today.
Okay, thanks.
Okay.
Okay, thanks.
Thanks again for the talk of Dr. Chao Liu.
Thank you.
Thanks.
Bye.
Bye.